Welcome again to the new lecture of the course, Fundamentals and Applications of Dielectric Ceramics. So, in the previous lecture, let's just recap the previous lecture. So, in the previous lecture we talked about, we started our discussion on dipolar polarizability. So, basically alpha D, so where we take the case that if you have electric field line like this, then dipoles are making a cones at an angle theta with respect to applied field. So, this is first cone, you might have another cone at another angle. So, basically all these dipoles then need to be, so this is an angle theta 1. So, you need to basically calculate the average dipole moment, which is basically total dipole moment of the system divided by number of dipoles. That is what we did. So, we took a slightly angular analysis considering the solid angle, and then we also took help of Boltzmann distribution function, which allows us to get the minimum free energy, because Boltzmann allows function said that number of dipole moments of energy u theta will be equal to A into exponential of minus u theta divided by kT. So, this avoids the calculation of entropy, which may be a little trickier. So, from this we calculated what is the average dipole moment. So, the average dipole moment was calculated as mu into beta, okay, and this beta was L beta, and this L beta was basically Langevin function, and Langevin function at low value of beta. So, beta will be equal to here mu E divided by kT. So, at low beta, that is low field or high temperature, we can approximate it L beta is equal to beta divided by 3, and from this we got mu E, which is equal to 1 over 3 mu square E divided by kT. Okay. So, from this we determined what is dipolar polarizability, which is alpha D, and this is 1 over 3 mu square divided by kT. So, what it means is that basically dipolar polarizability decreases as you increase the temperature. This is the analysis that we did, and this is dependent on temperature, unlike the other two polarizabilities that are electronic and ionic in polarizabilities. So, for example, if you do it for a system such as if you take for HCl, for example, so imagine that electric field is equal to about 100 megavolt per centimeter, dipole moment is about 10 to the minus 29 coulomb meter, then at a temperature of 300 Kelvin we get a beta of about 2.24, which is sort of okay, because we considered beta to be smaller than 1. So, this sort of validates the analysis that approximation was not wrong. However, if you do, for example, at a temperature like 30 Kelvin, then this increases the beta value to 2.4. So, that sort of invalidates our analysis, but what happens is that at 30 K HCl, so at this form HCl is liquid, right. So, all the dipoles are randomly oriented, but here HCl becomes solid. So, basically in solid form, if you have this kind of situation, the dipoles tend to cancel each other. It becomes a basically you have ionic polarization only that contributes. So, as a result, the dipolar polarizability is not valid at lower temperatures, it is only the ionic polarization that contributes for the HCl, because it is in solid form. So, sort of NaCl structure it makes. So, now let us so what we have done, just to summarize now, you have three polarizabilities. You have ionic polarizability, putting everything together, which is alpha electronic, which is basically proportional to R cube, but is not a function of temperature. sorry, electronic, it is electronic. Then we have ionic polarizability. So, this is electronic polarizability is true for every system, because every system will have atoms. Ionic polarizability is only for ionic solids, where we have cations and anions. In the solid form, there we consider alpha I, and this is proportional to 1 over y, but again it is not a function of temperature. Electronic, and then we have dipolar polarizability. This is for polar molecules only, where molecules have dipole moment. There we define this as alpha d, and this is proportional to 1 over T. So, this is a function of temperature, and it decreases as the temperature increases, which means you need to apply larger field to polarize the system. Okay. So, that is why you will see in every system the polarization decreases as you increase the temperature, in whether it is a ferroelectric system, piezoelectric, pyroelectric system, or any other system. The thermal randomization takes over as you increase the temperature, and as a result you have decrease in the polarization or dipole moment of the system. So,
can we here infer about the strength required to polarize a material?
Can we
infer here from the dipolar polarizability and how much strength is required?
Yeah, I mean, so basically this analysis should be reasonably correct if you have if you know the value of T, and if you wanted to create certain sort of some sort of dipole moment, then you can to some extent get a feel of what should be the electric field that you require to polarize the system to create some amount of dipole moment. So, as I said, P is equal to n mu square E divided by 3 kT. So, but this is not valid for nonlinear effects where you have interaction between the dipoles. So, here we are assuming that dipoles are non-interacting, okay. But if dipoles start interacting, then it is a different situation. But yeah, to a first approximation for a system where you have non-interacting dipoles, you can do that. And in a normal solid, you will also have effect of grain boundaries as well as defects that sort of complicate the scenario. But yeah, I mean, it may give you an idea of what is that which is required to polarize the system. Now, let us move on to, so what we have done until now is that we have looked at the basic dielectric properties, what is polarization, what is the mechanism of polarization, what is dielectric constant, and what is the frequency dependence of dielectric constant as a function of and looked at in the context of various mechanisms, which mechanisms are operative in which frequency range. And then we looked at a parameter called as polarizability and its analytical treatment, and we found that ionic and electronic polarizabilities are independent of temperature, whereas dipolar polarizability for polar molecules is dependent upon temperature. So, what we are going to do now is that we are going to look at the frequency dependence of these dielectric properties in a little bit more detail, because this is what is of interest practically speaking, because most dielectrics are used in applications requiring certain frequencies of electric field. So, now our discussion will be towards studying frequency dependence of dielectrics. So, here I mean the first thing that we are going to look at some fundamentals. So, we will first look at the comparison between ideal and real. So, this gives you basically good information about how good your dielectric is, how close are you to making a real dielectric. Basically a real dielectric is something where dielectric by nature should be insulator. So, which means there should be no whatever electric field you apply to it, all the electric field should be used in creating dielectric displacement, that is the polarization, and you should not lose any charges out from the system. But systems are not perfect, they have various defects and things like that. As a result, whatever current you produce should be charging current ideally, but it is not charging current. There is a component which is called as leakage current that is produced, and as a result some of the charges that you polarize leak out of the system. As a result, you have loss of information or loss of anything in terms of charges. So, this is what is important. This is what makes it important to understand the frequency dependence of dielectrics, because it gives you parameters which can be depicted in the form of frequency dependent behavior. So, let us look at first the behavior of a real dielectric. Alright. So, basically for most applications we do not require a static or DC field. For most applications require an AC field, okay. So, which means frequency is not equal to 0, it is finite, and as a result, so let us apply first, let us so the field is a sinusoidally varying field. Let us say the field is V is equal to V naught into exponential of I omega t, okay. So, if V naught is V is equal to V naught exponential I omega t, and if we apply this voltage to a dielectric, this leads to, so apply it to a dielectric, and this should give you what we call as charging current, and this charging current is basically the rate of change of charge, basically dq by dt. So, this IC is nothing but dq divided by dt, and we know that q can be written as C into dV by dt. So, this will be equal to I omega into CV, okay. And if you now do a little bit of, so this is omega C into V naught into exponential of I omega t, and let us say I add a factor exponential of I pi by 2, okay. So, this will become, I can write this as omega C into V naught into exponential of I into omega t plus pi by 2, alright. What does this mean? This means that this term pi by 2 basically means that the current, the charging current in a dielectric leads the voltage by an angle 90 degree or pi by 2 in a perfect dielectric. So, for a perfect dielectric, if you now make the phasor diagram as we call it, if this is the voltage vector, then the current leads the voltage by an angle 90 degree, and this is, okay. This is what is a simple current voltage relationship for a perfect dielectric. So, this is for a perfect dielectric where the current leads the voltage by 90 degrees. So, as long as the current is at certain angle at a voltage 90 degree, it is perfect dielectric. In reality, what you see is that in reality the current does not lead the voltage by, it leads the voltage by a angle theta. As a result, there are two components. One is this component which is in the charging current direction, and then you have another component, sorry, just I can draw it here maybe. So, this component is a charging component, and this component is within the direction of voltage is the loss component, the ohmic loss component, because for a ohmic loss, when the current is in the direction of voltage, which means it is a ohmic current. When the current is in the direction perpendicular to the voltage, it is a charging current. So, total current has now two components for a real dielectric, and that is what we will see how it comes about. How do you have, so anyway, so for a perfect dielectric, basically the current leads the voltage by 90 degree, and this is total current, and this all of this current is basically charging current. Okay. And what is the now in such a dielectric, what is power dissipation? So, power dissipation in such a dielectric would be, so instantaneous power that is drawn by the dielectric is basically IC into V. Okay. So, the time averaged power now that is P average is 1 over time period, integration over the time period into IC into V into dt. Okay. So, this is the time averaged power, where time period is given as 2 pi divided by omega. Okay. So, omega is the frequency of applied field. So, for an ideal dielectric, so I can probably write it here just to save some space. So, this is given as 2 pi divided by omega. So, for an ideal dielectric, with no loss of charging current, basically ideal dielectric there is no loss of charging current, no charges are lost. So, basically the current you have is only charging current, we do not lose it in some other form. The power dissipated must be equal to, and what is it? This is equal to 1 over time period integrated to form, this is from minus omega c into V naught square sin omega t to cos omega t into dt, that is equal to 0. Okay. You can write it in exponential forms whatever you want, but this is, so if you take V is equal to V naught sin omega t, then you can calculate IC from this. So, that will be sin omega t will plus pi by 2. So, as a result you will have sin pi by 2 cos pi by 2 factors, sin omega t and cos omega t, but you can also write this in the form of exponential form and you will get the same answer. So, this power loss, this power average power dissipated in an ideal dielectric should be equal to 0 for a. So, what it means is that during the first cycle when you charge the capacitor completely, the second cycle discharges the capacitor without any loss of charge. So, during the first cycle, so if this is the cycle you have, this is the first cycle, the charging cycle and the discharging cycle, the charging cycle and the discharging cycle. So, the charge in is equal to, so Q in is equal to Q out. There is no loss of charge, that is what it means by a, so basically it is like a perfect oscillator or you know the swing or a spring, whatever, there is no damping in the system, there is no loss. So, there is no loss in the system, which means it is a perfect dielectric, but life is far from being perfect, there is no dielectric which is perfect. So, as a result you have losses in the in every system. And so, when you have losses in every system, how do we depict it? So, anyway, it was necessary to show how a perfect dielectric would look like, so that we have something to as a reference, but let us see now how the behavior of real dielectrics look like. So, real dielectrics now. So, real dielectrics under alternating field. So, as I said, in real dielectrics generally what will happen is that, as I, so if you make a phasor diagram, let us say, and these phasor diagrams are very useful. So, let us say this is real, this is imaginary. Okay. So, we draw a voltage And this, as we said, that for a real dielectric, for an ideal dielectric, the I must be equal to, I must be perpendicular to V. So, this is I, this is V, IC, okay, is for a real dielectric. So, IC is equal to I total for a ideal dielectric. All right. Now, let us say for a real dielectric, the situation is something like this. The current is at certain, so and this angle is 90 degree, by the way. So, for a real dielectric, let us say this is your I total, and this is at certain angle theta. Okay. So, it has two components. The first component, that is parallel to, so this is the IC component. So, this is charging component, and this would be the what we call as loss component. So, this is I L. So, it's made of two terms, one is I C plus second is I L, and this is I total, and basically this is what is going to give you the voltage, and this is what is going to give you the current on this side. So, let us see. So, basically what happens in real dielectrics is, in addition to, so IC will be the charging current, IL will be the loss current, and this loss is basically, it happens because of various things. It could happen because of ohmic conduction of charges, in addition you may also have frequency dependent losses. Okay. So, ohmic conduction means there is no frequency dependence because it is in phase. So, generally ohmic component of the loss is depicted as frequency independent component of loss, but in addition to frequency independent loss, there is a possibility of frequency dependent losses, such as dipoles rotate in a system. When the dipoles rotate in the system, they consume energy. You may have traps in the system, you may have defective charges in the system which may keep the dipoles bound. For example, if you have grain boundaries have positive and negative charges, they have certain defects. These defects may pin down the dipoles may require more energy to rotate, or the amount of charges that you have stored as a result of, when you apply voltage, you create the movement of charges. But these defects, the extra charges which are there in the system, they may trap the charges that. So, you said that for an ideal Q in was equal to Q out during charging discharging cycle, but if this is not equal to Q in and Q out, which means this some delta Q, it could either get lost because of ohmic processes, or it could get lost because of frequency dependent phenomena. So, you have both the components of loss current. So, that is what we will see in the in our analysis. So, let us say we have both the contributions. So, we have I total, this will have I charging, I loss, some of this component will be frequency ohmic, and some of this could be non-ohmic and frequency dependent. So, this is frequency independent. Okay. So, or time dependent, you can say I total. So, let us say if so the loss current in these systems is given as what we call as G omega AC plus G DC into V, and since both of these are in phase with the applied field, that is why it is called as loss current, and this G is basically called as conductance. So, this is basically written in either mho or Siemens, and this is nothing but inverse of resistance, right. We know that V is equal to IR, so it is nothing but inverse of resistance. Okay, so the total current as a result IT is sum of charging and loss current and this is equal to IC plus IL, and this is equal to, so IC was I omega C plus now G omega AC plus G DC into V. This is what total current is, and here this so this angle, as we say, this angle is often, I have written theta, you can also write as delta in some language, and this is basically, this delta is called as dissipation factor. So, you can see that if you look at this delta, this will become 90 minus delta. So, tan of 90 minus delta will be equal to I loss divided by I. So, basically you can say that this angle will be here, you can say the loss angle. Higher the loss angle is, more the loss current will be, right. So, let us say if this was equal to some angle, let us say, sorry, let us say if we do not write it as delta, we write this as tan minus 90 minus theta, let us say we write this as delta, then this tan delta will be equal to IL divided by IC, and more the loss in the system, higher the tan delta will be for that system, or the more the power is dissipated or lost, charges are lost. Okay. So, we will do and if you have this as 0, which means there is no loss in the system. So, we will do more analysis of this in the next class, we are now running out of time. So, this will lead us to what we may expect as frequency dependent or permittivity, as we will see later on. Okay. Thank you.